Look up at the stars tonight. If you are far from city lights, you see thousands of tiny glowing points scattered across a deep, black void. To our eyes, the universe looks totally random. But here is the massive, mind-bending secret. The universe isn't a disorganized mess. If you could zoom out far enough past our sun, past the Milky Way, and past our neighboring galaxies, you would see that every single galaxy is part of the largest structure in existence. We call it the cosmic web. Everything in the cosmos is connected by giant, glowing filaments that stretch across millions of light years. Galaxies aren't just floating aimlessly. They are tracing a map that was laid down at the very beginning of time. Ask yourself this: why doesn't the universe just look like a smooth, even fog? In our daily lives, if you blow a cloud of smoke or steam, it eventually spreads out until it's just a faint haze. But the universe did the exact opposite. It started relatively smooth and then became clumpy. This structure, the cosmic web, is what allows us to exist. Without these giant filaments of matter, the gas needed to build stars would have remained too thin to ever collapse. Our Milky Way is just one tiny island universe sitting on a massive invisible dock. Understanding why galaxies form this web is like finding the ultimate blueprint for reality. It shows us that the cosmos has a logic, a skeleton that holds everything together against the expansion of space. So what are we actually looking at? When astronomers use powerful tools like the Hubble or the James Webb Space Telescope, they don't just see individual galaxies, they see them grouped into colossal structures. The most important of these are the filaments. Think of them as cosmic highways. These filaments are made of gas and stars, but they are mostly made of something we cannot even see: dark matter. These strands are millions of parsecs long. They bridge the gaps between massive galaxy clusters, creating a network that looks almost like a neural pathway in a giant brain, or a spiderweb covered in dew. Each drop of dew on that web is a galaxy containing hundreds of billions of suns. This realization challenges our intuition about gravity and motion. We usually think of gravity as something that pulls things into spheres like planets or stars. But on the scale of the entire universe, gravity is a much more complex architect. It doesn't just make balls of gas, it makes long, thin threads. Why matter collapses into these specific strands instead of just big clouds is a question that takes us back to the first second of the Big Bang. It involves a battle between the energy pushing the universe apart and the gravity trying to pull it together. In this video, we are going to break down how this web was built, why the universe isn't random, and what this giant skeleton tells us about our origin. To understand the cosmic web, we have to define its three main parts: the nodes, the filaments, and the voids. If the universe is a city, the nodes are the bustling downtown centers, the filaments are the highways connecting them, and the voids are the vast, empty countryside in between. The nodes are the most crowded places in the cosmos. These are galaxy clusters, like the Perseus cluster, where thousands of galaxies are packed together by intense gravity. In these nodes, the density is so high that galaxies are constantly colliding and merging, creating enormous elliptical monsters like M87. Everything in a node is held in a tight gravitational grip. Connecting these nodes are the filaments. These are the giant filaments that trace the mass of the universe. They are not just lines of galaxies, they are also cosmic waterfalls of gas. We have discovered threads that are 50 million light-years long. These filaments act as the plumbing system of the universe. Cold gas flows along these strands, funneled into the centers of galaxies to fuel the birth of new stars. If you lived on a galaxy in the middle of a filament, you would see a line of bright neighbors stretching across the sky, while in other directions there would be nothing but total darkness. Then there are the voids. This is perhaps the most surprising part of the cosmic web. Voids are vast spherical regions of space that contain almost nothing. They are the empty space that makes up the majority of the universe's volume. While a filament might be packed with gas and dark matter, a void is a graveyard of matter. If you were in the middle of a major void, the nearest galaxy might be so far away that your night sky would be completely black. The formation of these voids is just as important as the formation of the galaxies themselves, because the web is a zero-sum game. As gravity pulls matter into the filaments and nodes, it empties out the regions in between. Why does this matter for us? Our Milky Way lives in a relatively quiet neighborhood, but we are still part of this structure. We are moving within a local group of galaxies that is being pulled toward larger nodes. Everything in space is in motion, and that motion is dictated by the shape of this web. The web is the ultimate reference point. We use the cosmic microwave background, the light left over from the Big Bang, to measure the speed of galaxies as they travel through this network. By mapping the web, we are mapping the flow of energy and matter across 13.8 billion years of history. It is the most comprehensive picture we have of how the universe evolved from a hot, dense point into the complex network we see today. One of the biggest questions in astrophysics is why matter collapses into strands instead of clouds. If you have a big, irregular cloud of gas and you let gravity take over, your intuition probably says it should just shrink into one big, round blob. But that's not what happens on a cosmic scale. Gravity is a greedy force, but it's also very specific about how it pulls things together. In the early universe, matter wasn't perfectly distributed. There were tiny overdensities, spots that were just a little bit thicker than the space around them. When gravity starts acting on an irregular shape, it doesn't shrink all sides at once. It collapses the shortest axis first. Think of it like squashing a loaf of bread. If you press down on it, it becomes a flat pancake. This is the first stage of cosmic structure formation, the Zeldovich pancake. Once the matter has collapsed into a flat sheet, gravity then works on the next shortest axis, pulling the edges of the pancake inward until it forms a long, thin string, or filament. Finally, the matter flows along those filaments to the points where they intersect, which are the nodes. This step-by-step collapse is why the universe looks like a web rather than a collection of spheres. The strands are a middle stage of a long process where matter is trying to find the path of least resistance to the nearest gravitational trap. This process is driven by the fact that gravity is purely attractive. In ordinary matter, the electromagnetic force can push things away, which is why your chair stops you from falling to the center of the Earth. But gravity has no anti-gravity to stop the collapse. On a cosmic scale, the only thing that can fight gravity is the expansion of the universe itself. In regions where there is enough mass, gravity wins the tug-of-war and pulls the gas into these sheets and strands. In regions where there isn't enough mass, the expansion of space wins, stretching those areas out into the giant voids we talked about earlier. The role of gas in this collapse is also unique. Unlike dark matter, which just passes through itself, gas can collide and heat up. As matter falls into these filaments, it creates friction. This friction turns gravitational energy into heat and light, which we can observe as X-rays. This gas is the baryonic material that eventually forms the stars we see. But the gas is just a passenger. It is following a path that was already cleared by something else. To truly understand the cosmic web, we have to look at the invisible architect that set the foundation for the entire universe, the dark matter scaffolding. If the galaxies are the lights on the cosmic web, then dark matter is the wiring and the building frame that you can't see. About 90% of the matter in our galaxy and the vast majority of the universe is dark matter. It is invisible because it doesn't emit, reflect, or absorb light. We only know it's there because we can see its gravitational influence on the things we can see. For instance, if dark matter didn't exist, the stars in the Milky Way would orbit much slower than they actually do. The gravity of the visible stars isn't enough to hold the galaxy together. There has to be a massive, invisible halo of dark matter providing the extra pull. The cosmic web is essentially a map of dark matter. In the early universe, dark matter was the first thing to start clumping together. Because it doesn't interact with light, it wasn't pushed around by the intense radiation of the Big Bang like normal gas was. It was able to start building the gravitational traps while the rest of the universe was still a hot, chaotic soup. These dark matter clumps formed the original scaffolding. Once the universe cooled down enough, the normal gas, the baryons, began to fall into these traps. The gas collected and collapsed within these dark matter halos to form the first stars and galaxies. This is why we say galaxies trace the filaments. The galaxies are only where they are because they were pulled into the pre-existing dark matter strands. Astronomers have actually been able to create maps of this invisible scaffolding by using a trick called gravitational lensing. When light from a distant galaxy passes through a filament of dark matter, the gravity of that dark matter bends the light, just like a lens in a camera. By looking at how the light is distorted, we can see the shape of the dark matter filaments even if they are totally dark. These maps show that the dark matter is concentrated exactly where the cosmic web's filaments are. This scaffolding is what determines the age limit of the universe's structures. The web is a dynamic, evolving system. Over billions of years, the dark matter continues to pull more and more material into the filaments. Some scientists even propose that the center of our own galaxy might not be a black hole, but an immense concentration of dark matter particles called darkinos. While most believe Sagittarius A star is a supermassive black hole, the fact that dark matter is so dominant in our structure shows just how little we know about the web's true nature. Dark matter is the invisible king of the web, dictating where every star is born and where every galaxy will end up. One of the most fascinating aspects of the cosmic web is that voids, filaments, and clusters form together in a single, unified process. You cannot have one without the others. It is a cosmic tug-of-war where every winner creates a loser. When a high-density region, a node, starts to pull in matter, it has to get that matter from somewhere. It sucks the gas and dark matter out of the surrounding space. As the clusters grow larger and more massive, the space around them becomes increasingly empty, forming a void. This is why the web looks so sharp. The density differences are being pushed to the extreme by gravity. Think of it like a sponge. A sponge is a single structure made of solid material and empty holes. In the cosmic web, the solid parts are the clusters and filaments, and the holes are the voids. This structure appeared because of a process called bottom-up formation. Small clumps of matter formed first, which then merged to form larger and larger systems. Our own Milky Way has swallowed more than a dozen smaller galaxies in the last 12 billion years to reach its current size. Every time a galaxy is consumed, the web becomes a little bit more concentrated and the voids become a little bit more empty. This formation process is also what powers the most energetic objects in the universe, quasars. As gravity pulls gas from the filaments into the centers of massive galaxies, the gas spirals into supermassive black holes. This accretion process is incredibly efficient at converting mass into energy, much more efficient than the nuclear fusion that powers the Sun. This energy is so powerful that it can outshine an entire galaxy of 100 billion stars. But there is a catch. The energy from these black holes in the form of powerful jets can actually push gas away from the galaxy. This creates a love-hate relationship or a symbiotic relationship where the black hole regulates the growth of the galaxy and the surrounding web. If the black hole gets too greedy and eats too much gas, the resulting energy blast clears out the neighborhood, stopping the formation of new stars and preventing the galaxy from growing any larger. This feedback process is what prevents the cosmic web from collapsing entirely into a few giant black holes. It keeps the filaments fed but not overstuffed. The voids remain empty because the energy from active galaxies helps keep the gas from settling back into those regions. The entire web is a perfectly balanced machine, using the most destructive objects in the universe, black holes, to maintain the delicate structure of the filaments that allow life to exist on small rocky planets like ours. How can we be so sure about a structure that is mostly invisible? The answer lies in the incredible power of supercomputers. Scientists have created massive models like the Millennium simulation to see if our laws of physics can actually produce a cosmic web. In these simulations, they put in the starting conditions of the Big Bang, the temperature, the density, and the ratio of dark matter to normal matter. Then they let the virtual universe run for 13.8 billion years to see what happens. What they find is almost identical to what we see in the real sky. The computer produces the same filaments, the same nodes, and the same vast voids that we observe with our telescopes. But there are some key differences between what simulations reveal versus what we observe. For one, simulations show us the full picture, including the dark matter scaffolding that we can't see directly. When we compare these to our luminous maps of galaxies, we find that the galaxies are only the peak of the structure. There is a lot of missing matter in the real universe that the simulations say should be there. This is one of the reasons astronomers are so obsessed with finding invisible galaxies, galaxies so full of dust that they are completely hidden in visible light. These dinosaur galaxies were discovered in the 1990s using sub-millimeter cameras, and they filled in a major gap in the cosmic web. Simulations also help us understand the pacing of the universe. In the computer, we can see that big galaxies crashing together is relatively rare. However, we observe these events happening more often in the early universe. This tells us that the active phase of the cosmic web was much more intense in the past. Quasars were about 100 times more common 10 billion years ago than they are today. The web was vibrant and violent in its youth, and it is slowly calming down as the voids expand and the fuel runs out. The simulations act as a time machine, letting us see the high-speed version of cosmic history. One of the most impressive feats of modern astronomy was the Event Horizon Telescope image of the black hole in M87. Before we took that photo, we had only simulations of what a black hole would look like. When the real image came back, it was a near-perfect match for the theoretical models. This gave us massive confidence that our understanding of gravity is correct, even in the most extreme environments. It proves that the logic we use to build the virtual cosmic web is the same logic the real universe uses to build itself. We aren't just guessing, we have a confirmed blueprint. One of the biggest rude awakenings in cosmology was the discovery that the cosmic web isn't a new structure. It didn't take 13 billion years to form. Instead, we have evidence that massive black holes and structured galaxies were already present only 800 million years after the Big Bang. In the grand scheme of the universe's life, 800 million years is like a wink or a snapshot. Why this structure appeared so early is a major puzzle because, according to simple models, it should have taken much longer for gravity to pull so much matter together. This discovery has forced us to change our entire story about the early universe. The traditional idea was that small stars formed first, then they gathered into small galaxies, which then slowly merged over billions of years to form the web. But the early arrival of massive structures suggests that the gravitational traps were much stronger than we thought. This brings us back to the Big Bang. The initial overdensities in the mass distribution of the universe must have been there from the very beginning. These were the seeds of the web. Without these initial ripples in space, the universe would have expanded so fast that matter would have been spread too thin to ever form a web. This is where the theory of inflation comes in. Some scientists believe that in the first fraction of a second, the universe expanded extremely rapidly. This rapid expansion would have amplified tiny quantum fluctuations into the massive overdensities that became the nodes and filaments of the web. This explains why the web is so synchronized. It's because the foundation was laid down before the different parts of the universe were ripped away from each other by expansion. The cosmic web is essentially a fossilized record of the very first moment of existence. This early formation also explains why supermassive black holes exist. We don't really know how a black hole can grow to be 1 billion times the mass of the Sun in such a short time. There are no stars large enough to collapse into a black hole of that size directly. One theory is that they didn't come from stars at all, but from the direct collapse of huge clouds of gas in the early universe. If a gas cloud is dense enough, it can bypass the star phase and go straight to a black hole. These primordial monsters would have acted as the anchors for the web's nodes, pulling in galaxies and filaments much faster than anything else in the cosmos. What does the cosmic web ultimately tell us? The cosmic web tells us about the universe's origin in a way that individual stars never could. It shows us that the universe started in an incredibly ordered state, or what scientists call low entropy. If the Big Bang had been a truly chaotic explosion, the matter would have been thrown out in a disorganized mess, and the web would never have formed. The existence of the web is proof that the Big Bang was a highly specific, synchronized event. Every filament we see today is a direct descendant of a ripple that existed 13.8 billion years ago. The web also reveals the composition of our origin. By studying the way galaxies are distributed along the filaments, we can calculate the exact ratio of dark matter, dark energy, and normal matter. We have found that the normal matter we are made of, the stuff that forms visible things like you, me, and the stars, is actually a tiny fraction of the total energy budget. The web is dominated by dark energy, a repulsive force that is currently causing the expansion of the universe to speed up. This dark energy is the reason why the filaments are being stretched and why eventually the web itself will be torn apart. This structure is a multi-messenger source of information. We don't just learn from light, we learn from neutrinos and gravitational waves produced by the events within the web. When two black holes merge in a node, they send out ripples in the fabric of space and time. These waves travel across the filaments and arrive at Earth, bringing us information from the dark side of the web. We are moving into an era where we can hear the web as well as see it. This will give us our first real look at the first second of the universe's life, before the first light could even travel freely. The cosmic web is the ultimate story of evolution. It shows a universe that is dynamic and violent, not static or peaceful. It is an extreme astrophysical laboratory where the laws of physics are tested to their breaking point. Every star that explodes in a supernova, every black hole that launches a relativistic jet, and every galaxy that merges is a part of this grand cycle of creation and destruction. We are the children of the universe, born from the ordinary chemicals forged in the hearts of stars that were themselves birthed by the filaments of this web. The web is our home, our history, and our future. We have seen that the cosmic web is the supreme architecture of the cosmos, but it is not eternal. Just as black holes eventually evaporate and stars run out of fuel, the web has its own expiration date. The very same force that made the universe flat and stable, dark energy, is now the force that will destroy the web. As the universe expands faster and faster, the space between the nodes is stretching more rapidly than the gravity can pull things together. The filaments are being thinned out and the voids are becoming truly empty. Eventually, the expansion will exceed the speed of light for almost everything we can see. Galaxies that are currently part of our local neighborhood will be pushed beyond the cosmic horizon, becoming invisible forever. Trillions of years from now, the Milky Way and Andromeda will have merged into a single Milkomeda galaxy. But that galaxy will be a lonely island in an infinite, dark void. The filaments of the cosmic web will have snapped, and the great highways that connect the universe will be gone. Future astronomers wouldn't even know that other galaxies ever existed because the web would have been completely erased by the expansion of space. This reality shows us that we are living in a very special time in history. We are in the Goldilocks era of the web. The universe is old enough to have formed complex structures and intelligent life, but it is still young enough that we can see the filaments and the light from the Big Bang. We can still map our origin and understand our place in the network. Every time we observe a distant quasar or a shimmering band of stars, we are witnessing a cosmological clockwork that is slowly winding down. The web is a temporary bridge between a hot, dense past and a cold, dark future. If you want to understand space like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. Understanding the cosmic web is the first step to understanding the ultimate fate of everything. It shows us that gravity is a patient collector, but expansion is a relentless divider. The balance between these two forces is what defines our reality. The web isn't just a pattern of galaxies, it's the signature of a universe that is growing, changing, and eventually fading away. But as the web stretches, it reveals something even weirder about the speed of things in the deep universe. Why do the galaxies on the edge of our vision seem to be running away from us so much faster than our neighbors? It's not just random motion, it's a fundamental property of the web itself. If you want to understand why the farther a galaxy is, the faster it rushes away, and how the universe can expand faster than the speed of light without breaking physics. Click here to Why Farther Galaxies Move Away Faster video.